So welcome everyone to the Theoretical Astrophysics seminar. This week is a special seminar on Thursday rather than Friday. We are very happy to have Elena Rossi from Leiden University being our speaker today. Unfortunately, she could not be here in person, so we will invite her another time soon to be here in person. Elena comes originally from the same university that I come from. So she studied physics at the University of Milan, but then she moved very soon for the PhD, which she did in Cambridge under the supervision of Professor Martin Rees. And so she worked with Martin on gamma ray burst at the time. So she started out on high energy theoretical astrophysics, but as I will mention now briefly, she branched out in many other areas, and the talk of today will show that very clearly. So in fact, Elena, since then, she moved then in 2005 after the PhD, she moved to Colorado as a Chandra Fellow, working with Mitch Begelman. And then in 2008, she moved again to the Raka Institute of Physics at the Hebrew University in Israel. And then since 2010, she's been a professor at Leiden, and she has worked really on a large range of topics, from tidal disruption events to double white dwarfs, and also galactic center dynamics, hypervelocity stars, and even data mining using Gaia data, especially in the last few years, to search for unbound stars, so related to the topic of hypervelocity stars. And in the time that she was in Colorado, she also started working on more exotic objects such as quasi-stars, and to develop the interest in general in the growth of supermassive black holes. And then she was very early joining the effort of the LISA consortium as one of the leading theorists inside the LISA consortium. And in fact, she has various leadership roles inside the consortium, including being one of the leaders in the LISA science group. And I can only say, by being also part of the consortium, that she has been doing a tremendous work in that role as well. And she has pushed a lot within LISA and in general the notion of multi-messenger astrophysics, so especially combining gravitational waves with multi-wavelength electromagnetic observations to extract astrophysical information. And today the talk is in that context, and the title is by messenger map of the local group of galaxies. I let Elena now starting her speech.
Thank you very much, Lucio, for the very nice introduction. And I'm really sorry not to be there, but I'm also very excited to be able to share anyway my work in this remote mode. So the research I'm going to talk about today has the ultimate goal to deliver a robust measurement of the mass distribution of our galaxy and the local group of galaxies, and also of other properties, for instance, the star formation rate and so on. And like broadly speaking, I'm pursuing 3 different lines of research towards this end. One is using stellar streams to determine the dark matter content and mass distribution in our galaxies, hypervelocity stars for the same goal. And instead, when it comes to the distribution of baryonic matter, this is something I'm looking a little bit more at the future, using LISA data in synergy with optical and infrared observations. So in this talk, I won't talk about all these 3 lines of research. I have selected streams and gravitational wave observations. Okay, so every talk on galactic dynamics must start with this beautiful stellar map of the sky from Gaia early data release 3. This is amazing. It's the largest stellar map ever produced. And even by eyes, you can see on the your right bottom, the large and small Magellanic Cloud. But these are only the most massive, closest neighbors. The local group of galaxies is made of many more dwarf galaxies, and also by a big, the most massive neighbor is the Andromeda galaxy, or M31, that you see again in the bottom right here in this schematic. So the Milky Way and the local group of galaxy are a tremendous laboratory for astrophysics and fundamental physics because of the richness of data, especially since Gaia came along, but not only. Informations have been used to understand the assembly history of the galaxy and the local group. For instance, testing Lambda CDM model and testing alternative gravity theories as well. So how this is done? Many in the audience, and Lucio and his group, of course, they know the game is to basically take a cosmological simulation or zoom-in simulation of Milky Way like galaxies and compare with observations. Okay. The problem on the observational side is that the observational benchmark is not quite robust, not only uncertain, but really the systematics are making the work very difficult. For instance, this is an example of the determination of the total mass of our Milky Way, which we know is mainly in dark matter, and the dark matter halo extend out to a virial radius of, say, 200 kiloparsec. And this, the notion of what is the mass, the total mass of Milky Way is very, very important to select the correct simulation that you need to compare the simulation features with observations. And as you see in this plot, here is a compilation of measurement of the total mass of the galaxy by different methods and different dynamical tracers. You see that the Milky Way mass is uncertain by a factor of 3. Okay, but not only that. Look at the two highlighted here. I circled the two measurements from streams. You see, these are you know, quite, I mean, are relatively precise, but clearly there is a systematic, because two different streams give a very different mass of the galaxy, and the realization of a Milky Way like galaxy using these two different masses gives very different feature. So the problem is that in this factor of 3, predictions from simulation vary significantly, and therefore the inference from comparing simulation to data is very uncertain. We had in the past also contradicting conclusions. Okay, so what I want to do with my research is find ways to deliver robust measurements for the mass of the galaxy, but also for other properties. So really work first on the robustness and then on the precision of our observational benchmark using numerical tools. So let's talk a little bit more about measurement with streams. So when I talk about streams, I mean stellar streams, dwarf galaxies or globular clusters that falls into the potential of the Milky Way can get tidally disrupted by the tidal field of the galaxies. And once tidally disrupted, the stream of stars, you can think act like point masses in the potential, and so they become excellent dynamical tracers of the potential, therefore of the mass and mass distribution. In particular, streams are very powerful in constraining the enclosed mass within their average distance. Okay, but we do not model streams trajectories, which are highly dependent on the initial conditions on the progenitor. What we do is we use the fact that stellar streams, the stars in stellar streams, retain a memory of their progenitor in terms of the energy and angular momentum. Instead, all stars in a stream have a similar energy and angular momentum of the progenitor satellite, for instance. And here you see on the right a plot in energy and angular momentum for observed stars in the spectroscopic survey H3. And highlighted with color, you see the parameter space covered by streams, and you see that they are clumped. But when you measure the energy, when you infer the energy, sorry, you calculate the energy of a star, you need to assume a potential. Okay, so the idea is that streams clump in energy and angular momentum only if the energy is computed in the right potential. So maximum clumping is obtained in the correct potential. And basically this is the fundamental properties that we use. We determine the best potentials and the nearby best potentials by analyzing the clumping in action space of streams. Okay, so the first question that we ask is what is the source of the bias that we see in streams measurements? So on the left, you see one simulated stream from the fire simulation. This is from a work of Robin Sanderson, which is also a collaborator of mine. And the work that I'm describing is led by my PhD student, Stella Reino. So when we, for instance, fit for the circular velocity of the galaxy, so what you see in the right, circular velocity of the galaxy is a function of distance from the galactic center. When we use the entire stream, all the stars in the stream, then we have, unfortunately I don't have the plot here, but we have an excellent agreement, okay? But then we realized that actually observations are hardly of an entire stream. We most likely see a part of a stream, and even most likely we see a stream at pericenter because it's the portion of the stream closer to us. And this is, for instance, is the blue section on the leftmost plot. If you use only this pericenter portion of the stream to deliver a measurement of the circular velocity at the distance of those stars, then you have the blue point on the right, in the right plot. And you see that the mass is actually overestimated, and the circular velocity, the mass enclosed is overestimated, and therefore the circular velocity is overestimated. If instead you use another portion of the stream, which contains stars that are more between the pericenter and the apocenter of the stream, then you have a better agreement with the true potential. Okay. And the reason why the pericenter delivers worst results is that in that portion, stars have a large gradient in velocity, but in a small range of distances. So if you think about orbits, then many orbits can get through those points equally well, and each orbit would correspond to a different potential. So the constraining power is lower than stars instead between the apocenter and pericenter, in which the correlation between velocity and position span a large range in space and velocity. So in the phase space, it's a large portion of the phase space. Okay, so what shall we do? So our answer to the problem is actually to do the first time. So of course, we cannot observe the whole stream. So what we thought, okay, but if we combine measurement of different streams that hopefully are on different phase, are observed on different phase, and we fit them simultaneously, then the fit should improve. So what we did here is to take 3D, 6D data of the GD1 stream, orphan stream, and Palomar 5 stream. Okay, so in orange, I guess, is the constraint always on a circular velocity at from GD1 at the location of most of the stars of GD1. GD1, we know that is the portion that we observe is in the stars are at the pericenter, and you again see this bias. Okay, in yellow you see the constraint if we analyze only orphan data, and orphan data are of stars in the intermediate range between pericenter and apocenter, and Palomar 5 on constraints is in cyan, or I guess it's cyan. And stars are at the apocenter actually of their orbit. Then we instead simultaneously fit, so this free set of data, and the result is the pink shaded regions. Also, we select the potential that goes through the local standard of rest. I forgot to mention this, and the result is of the combined fit is the pink shaded line that shows the 1 sigma and the 2 sigma constraint. By comparison, we have plotted models of consensus model, if you want, for the Milky Way potential from Macmillan and Bovey, and the gray point are actually measurements. Okay, so it's clear that the fit joining different combining streams has tremendously improved. So the way forward is, of course, more streams at different distances. So also this is very important. Okay. And this, let's say, all I wanted to say about the streams. For us, the solution is combining multiple data sets. Okay, and we are working more on this. But not only the dark matter content of our galaxy is uncertain, also the baryonic content and their distribution is uncertain, more the distribution, I would say. For instance, here I'm plotting, so on the y-axis there is the scale height of the disk, and in the x-axis is the scale, radial scale of the disk, okay? And, and we have measurement from a collection of different tracers. And you see that they span a large range. There is a sort of a consensus around, for instance, a radial scale of 2, but with large uncertainty. Conversely, the other point that I circled, the yellow one, as it's more precise, but clearly there is a systematic effect there. Because the HR, the scale radius that measurement delivers, is more than 2 times larger. Okay, And why this is important? It's important because, for instance, by comparing simulations with the baryonic distribution of matter, we can understand better how star formation proceeds, for instance, and also feedback processes. Okay, so what is my way forward? Here is when I go actually thinking more about the next decade, and where I use my expertise in gravitational waves. In fact, my way forward is to use actually gravitational wave data in conjunction with optical data to trace the baryonic matter in our galaxy and outside. When I think about gravitational wave detections, though, I'm not thinking about detection from ground-based interferometers like LIGO and Virgo and CAGRA, but future detection with the laser interferometer space antenna. And here I'm showing in animation. This will be 3 satellites in flight formations trailing the Earth at an angle of 20 degrees or so. The satellites are separated by millions of kilometers, which implies that this effectively the laser interferometer is sensitive to the milli-frequency range. In this low frequency range, the most abundant sources that are present and that the LISA will detect are white dwarf binaries. White dwarf binaries not in the process of merging, but white dwarf binaries in the process of circling around each other, so in the in-spiral phase. So they come in mainly 3 flavors. The most abundant are detached double white dwarf. So 2 white dwarfs circling around each other. We think there are around 10 to the 8 such binaries in the Milky Way. Okay. Another flavor is instead a white dwarf paired with a main sequence star. And these are more likely in the process of exchanging masses. So the main sequence star is the white dwarf is accreting mass from the companion, and these are called CV, or cataclysmic variables. Another flavor is the white dwarf pairing with a helium core. So detached double white dwarf are the most abundant, but also are the deepest in optical, while CVs and helium core white dwarf binaries are actually the most are less abundant in numbers, but actually are the brighter in UV, X-ray, and also optical. Okay. So how many do we know now that it's certain that LISA will be able to see? So right now we only know of 11 systems that LISA will be able to see with high signal to noise within the first month of operation. So here what I'm plotting is on the y-axis the characteristic strengths or the signal, the gravitational wave signal from these binaries that we know very well from optical observations as a function of frequency. The black curve is the LISA sensitivity curve. So 11 of those binaries are well above the sensitivity curves, and that the one that I just mentioned. And as you see, most of them are not double white dwarfs, but are the other kinds of white dwarfs because they are brighter. Okay. When LISA will come along, actually, LISA will deliver tens of thousands. So from 11 that we know now to tens of thousands double white dwarf binaries, for instance, in Fourier observations. Specifically for detached double white dwarf binaries that are the most abundantly detected, we will foresee something like 26,000 detached double wide dwarf binaries with high signal to noise. And this is, and what I'm going to show here is mostly the work done by Valeria Corol, who was a PhD student with me. Now she's a Rubicon Fellow in Birmingham. Okay. Why do I think that double wide dwarf binaries can be excellent traces of the baryonic mass? First of all, because they're extremely abundant, as we just mentioned. In fact, they're the most common compact object in the universe. 97% of all Milky Way stars will become wide dwarf, and say half double wide dwarf. Then they are pervasive in the sense that their progenitors, which are relatively low mass, are everywhere in the galaxy, in the bulge, in the galactic center, even in streams and in outer galaxies. Also, double wide dwarf or wide dwarf binaries in general, they come from stars that have been born during a large stretch of time, like at least a few giga years. So they can give us information of what has happened in the last few giga years. Finally, wide dwarf are not born with a natal kick. So when where we observe wide dwarf or double wide dwarf is where they were born. So they can directly trace their progenitor stars. Finally, I will show that are so luminous that in fact we can see them through and in the Andromeda galaxies. So everywhere they are, we will see them, at least the most massive. Okay. And then why do I think that are excellent to be gravitational waveform double wide dwarf binaries are an excellent synergy with optical information. Because gravitational waves do not suffer from absorption, like for instance optical does, and do not care about crowding. For instance, this is a big problem for Gaia, stellar crowding. Moreover, I think even more, I will show that these two first points that I just mentioned means that we can see through the galactic center and even beyond, which is something that we cannot really do in electromagnetic wavelengths. But I think most importantly, through the local group, gravitational wave can deliver a single uniform way of determining the distances of objects and galaxies and wide dwarfs and streams. While I'm sure you know that the big problem within the local group is the distance scale, because we need to use very different methods. So nearby we use the parallax, and then farther away spectroscopic distances, and then photometric distances, variable stars, and all these distance indicator needs to be calibrated. So gravitational wave can deliver like a unique way of determining distance, homogeneous through the entire local group. Finally, gravitational waves with wide dwarfs trace the low mass stars, while optical or UV and X-ray data, they trace, in fact, a much broader range of stellar types. But when it comes to farther away galaxies, like the Andromeda, for instance, or even the Large Magellanic Cloud, then only very massive stars, so young stars, can be detected individually. What optical observation has, the gravitational wave data cannot provide, is the ability to give us the motion, proper motion, and radial velocities. And this is what I want to exploit mainly. the ability of gravitational wave to give us the distance, and the ability of optical data to give us the motion. And here I'm showing the first attempt to do this. This is a paper that we published also together with Enrico Barausse. Okay, so what I'm showing here, and I'm always like amazed when I see it, I think it's beautiful. It's a map of the galaxy in gravitational wave. So each point is a high signal to noise detection of the resolved binary. To put it in context, and this is also my vision for maybe in the 30s or 40s. This is a compilation of observations in different bands of the Milky Way. And then I added our view in gravitational wave. You see in particular that the bulge is very well determined with respect, for instance, look at the optical, where like dust is actually giving us a very patchy vision of the galaxy. The closest to what the gravitational wave can give is the near-infrared, for instance, but the number of resolved individual stars in gravitational wave is much higher. Okay. We can even appreciate this best if we put this map of resolved binaries in galactic coordinate. So at the 0, 0 is the galactic center. For comparison, in light blue, you see the binaries that we are detected and will be detected with Gaia and LST. They are all around the solar circle, let's say, maybe a couple of kilometers around the sun. The yellow and pink are instead the gravitational wave detections. You see that we can see through the galactic center, but also on the other side of the galaxy. So we can map the other side of the galaxy with respect to the sun. So what we did with these detections is to create mock data. Each error bar is basically determined by represent the standard deviation obtained from 10,000 realization of the white dwarf spatial distribution in volume within the LISA measurement errors, and then we plot one realization. So these are the pink plots with error, pink dots, sorry, with error bars. These are our synthetic data. Then we fitted this data with common models for the bulge and the disk, and we have derived the scale height and radial scale of the bulge and the disk. We can recover this within a few percent. This is, however, is assuming that we already know the underlying, we are using the correct model. However, we also tried to use the wrong model, and the fact that we have many detections not only towards the bulge but also on the other side of the disk towards the anti-center allow us, for instance, to easily discriminate between the two most popular models for fitting the disk, as I'm showing here. So
Elena,
yes.
Can I ask you very quickly? You are showing the fits to analytical models here of the potential.
Yes, sorry, yes. So this is the simplification. These are analytical model of the potential. In fact, the next step is instead to use simulation to do the same. I will show an example in a few slides. You're right, I didn't mention it. Okay, but this is basically what we can do in gravitational waves, mapping the shape, okay? But we don't know anything about the normalization. We don't, gravitational wave, we cannot really measure motions. because the Doppler effect is not big enough. We are not sensitive unless there are stars really close to the supermassive black holes. So what we did instead is to take our synthetic catalog of double white dwarf detected in optical. In particular, these ones are only the eclipse binaries for which we know everything. Because of the eclipsing, we know the radius, the separation, so we can determine very well other parameters. And then we mock observation, for instance, what would be the parallax with Gaia, what would be the proper motion with LSST, and so on. And we use this sample to determine the velocity, the circular velocity around the sun. And this is the plot, the upper plot. Okay, so with this small sample of double white dwarf, we have an indication of what is the circular velocity around the sun. And with gravitational wave, we have an indication on the shape of the disk and the bulge. So the next step was to perform instead a joint fit of these data sets. And this is the results. Our aim was to determine the masses. It turns out that we can determine accurately the mass of the bulge and with a decent precision of 17%. So this is extremely competitive with respect to other measurement method. But we do not do a good job when it comes to the mass of the disk. And this is because, basically our optical tracer in this example they can give only basically one measurement of the circular velocity around the sun. So the next step is to use other tracers like giant stars to be able to also infer the circle or streams. To be able to have firmer constraint on the halo, so at larger distance than 10 kiloparsec. So, and of course, then to use a more realistic potentials, not an analytical one. On that note, what we did is, we did the following. We thought, since gravitational waves are actually so good in looking through the galactic center, we ask ourselves how well they can actually trace the bar that we know is present in the galaxy, or even the spiral arms. Okay, the motivation is that in fact observational we don't know. We do not know. There are contradicting observational evidence on the number of spiral arms in the galaxy, or even if there are spiral arms in the galaxy. And the properties of the bar is actually hot topic. For example, the bar's viewing angle, so under which viewing angle we see the bars, if you look at in literature, the uncertainties, the measurement that has been cited goes from 10 degrees to 45 degrees in viewing angles. Okay, so what we did is this time to take a Milky Way like realization using an embodied simulation by Elena Maria. And this is the work of my ex-master student, led by my ex-master student, Martin Wilhelm. Okay, and here what I'm showing on the left is actually a snapshot of this innermost part of the galaxy, the innermost 10 kiloparsec, where you can clearly see, at least in this realization, the galaxy has mainly two spiral arms and a bar that extend out to 4 kiloparsec or so. Okay. Here instead, on the right, I'm showing again the detected double white dwarf binaries. In particular, this is the binary number density. Okay, so already by eye, you can see that, which you cannot do in electromagnetic wavelengths, you can see by eye the bar, but it's clear that the spiral arms are barely visible. And this is because spiral arms actually are not dense enough, while the bar is an actual overdensity. Okay, but to put more quantitative, what we can already assess by eye, we made a Fourier transform of this image on the right. And here I'm plotting the m = 2 mode that should be the most prominent if we have a non-symmetric structure like a bar and 2 spiral arms. Here in particular on the left, I'm showing the amplitude, the normalized amplitude of the m = 2 mode as a function of distance from the galactic center. The first large peak we identified with the bar, which means stars from both the bulge and the innermost disk. Then the blue curve is the total density profile of all masses, all particles in the simulations. And you see that there are like another peak. This is the spiral arm. The black point with error bars are only our synthetic gravitational wave data. So it's clear that we can reproduce the first peak, but the second peak, it's there, but the error bars are too large. So from the rising of the first peak, and that's what you see on the right, it's a zoom in on the rising, one can actually derive the axis ratio of the bar, the length over the width. And we show that we can reproduce this ratio of length over width within 1 sigma of what you would do if you would use the total mass distribution. If we look instead at the phase of the m = 2 mode, this is the plot. So phase is a function of distance from the galactic center. Sorry, the phase is constant up to, let's say, 4 kiloparsec, and this we think is really the footprint of the bar. And then it becomes very noisy when then the spiral arms kicks in. From how long this phase remain constant, we can derive the length of the bar. And actually from the value of the phase, we can derive the viewing angle. And this is the summary of our results. So what I'm showing here is a nice image of the innermost 6 kiloparsec of this simulation. This is a contour of density contour of the total mass. So what we are seeing is basically the bar and the 2 spiral arms getting out. The red lines are our measurement with gravitational waves with their uncertainties. So we derive the viewing angle, we recover the viewing angle within 1 degree, and the bar height quite accurately, I would say, and as well as the bar length. So next step in this direction is to use other kind of binaries as well, and also information from optical observations, which we haven't folded it yet. This is pure gravitational wave analysis, and we are working on that. So how much time do I have? Okay, yeah, perfect. So actually, this is all I wanted to say about mapping our own galaxy and the baryonic distribution with gravitational waves. What we did with Orlin Cope, which was it's my ex-bachelor student, now PhD student in Groningen with Amina Helmi, is look up from the galaxy and see what we can do for actually our neighbors. He showed that we can see white dwarfs, actually double white dwarfs, actually really everywhere in the local group. Then we focus on the Andromeda galaxy. So what I'm showing here, these plots are chirp mass of the binary, so the proxy for the total mass of the binary as a function of the period of the binary. Okay, the yellow line that you see, so on the left of the yellow line are detection that have a signal to noise greater than 7 at the distance of Andromeda. So those are detection of resolved binary in Andromeda. Okay, and the dots are how are our detections. Are the white dwarf binaries in Andromeda, the entire sample, color coded by signal to noise ratio. Okay, so it's clear that Andromeda is that the actual detection of double white dwarf in Andromeda won't be enough to map its structure. In 4 years of observation, we expect something like 10. In 10 years, several tenths. Okay, you can do something, but it's not enough to have a precise shape, investigation of the shape, for instance, as we did with the Milky Way. However, the interesting thing is that all these detections are of binaries which are super Chandrasekhar binaries. Binaries whose total mass is greater than the Chandrasekhar mass. And they are very, very tight binaries that will merge within 1 million years. Why this is important? Because we don't have a single detection in electromagnetic wavelengths of super Chandrasekhar objects. This is because very massive white dwarfs are very small because of their equation of state, are very, very small, so are dim in electromagnetic wave. Instead, in gravitational waves, they're very bright. So in fact, in this paper, we realized that gravitational wave may be and will be probably the only way in which we can detect and study the population of super Chandrasekhar systems that are thought to be progenitor of supernova 1A. But not only in the galactic center, not only in our galaxy, but in the whole local group up to Andromeda. This is impossible. Is impossible with electromagnetic observations alone. So the Milky Way is richness of data. Andromeda, not so much. So we turn our attention to the Large Magellanic Cloud, which is the most massive of the closest satellites of the Milky Way. And this is the beautiful image from Gaia EDR3 data release you see on the left. And the work is done by, I forgot the picture, by my student Michael Kane. In the Large Magellanic Cloud, we expect to resolve hundreds, maybe 600s, or between 200 and 600s of double white dwarf binaries. So this is actually enough, for instance, here is the picture, enough, for instance, to make a contour plot of gravitational wave flux. So what I did here, so the image below is Gaia, and the image above is a contour of gravitational wave flux. So what I had in mind are this beautiful picture of a galaxy, or a cluster of galaxies, in which there is the optical, the galaxies, and overimposed the radio maps. And so we have instead here the maps in gravitational waves. And Michael is working on making this map, analyzing this map together with the map in optical to derive the morphology, the distribution of baryons. Unfortunately, I don't have results yet to show for that, for the morphology, but I do have on another aspect, which is recovering the star formation history of the Large Magellanic Cloud, which again is largely uncertain. So on the left is the Magellanic Cloud, and on the right is the double white dwarf progenitor star formation rate as a function of look-back time. In blue, you have a star formation history which increases with time, from data, from optical observations and infrared observation, UV observations. On the other hand, for instance, in red, we have other proposed star formation. This one is the one in which there was a burst of star formation 10 to the 4 years ago, and then a low level of star formation afterwards. We wanted to see if through detection of double white dwarf, we could distinguish between, for instance, these two extreme star formation history. So the result is that indeed we can, because both the total detection and the total detection of massive binaries are very different, are statistically different. For instance, for an increasing star formation rate, we expect over 600 detection. Even within the area of the realizations are statistically different. With respect to the 300 is expected in the case of a burst of star formation long time ago. But to be even more quantitative, we actually analyzed the distribution of masses and period of binaries in these two different cases. And yes, we showed statistically that can be distinguishable. So I think it's an alternative way to map the history of the galaxy that has, again, a lot of potential. And I think this is everything I wanted to say. There is more that we are doing, so I hope to come back again to show my results. Thank you. You are muted, Lucio.
I wanted to thank you also for the very nice talk, and we can thank you virtually also with a clap.
Thanks.
And yeah, so I guess we have some time for questions. I see if people want to start. I have some questions, but I wanted people to start first from the audience. Okay, who wants to go first? Maybe some of the students. Okay, well, I will break the ice then, if nobody wants to break the ice. So I was wondering, putting together the part where you discuss the streams and the part on the bi-messenger analysis. And when you show the models of Elena, Dongia, and the feeds that you can get to the galactic structure, could you actually use the white dwarfs themselves, the double white dwarfs, to infer the phase space structure of the galaxy in the inner 10 or 20 kiloparsecs? Mainly, if you don't have a smooth baryonic distribution like the one that you use from Elena simulation, so instead of having just the bar and the bulge, you also have superimposed some very weak disturbances due to old streams that are hidden. Is there a way to find them, maybe using the same technique?
Yeah, so that's a good point. Also, because we think that a large fraction of the stars in the galaxy now we think it comes from Enceladus or Gaia sausage.
Yeah.
So yeah, that's a good question. So the proper answer should be I don't know, because we haven't tried. But what I think is that it is possible because it is in principle possible because of the things I just showed. So I think it is possible to distinguish between different. Not only density over densities, we can distinguish over densities, single out over density, but probably we can also distinguish between two different populations that have different star formation histories.
Okay.
So if a stream, large stream, of course, like Enceladus, had, as we think, a very different star formation history than the Milky Way, then it will come with its own white dwarf binary population, which will have an overall different period and mass distribution. But this is a very interesting question, and needs to be explored, actually. Yes.
Thanks. I see now several hands are up. I think Pedro was the first one.
Hi, Elena. Thanks for a great talk. So I have a question about hypervelocity stars. So you said that the main way forward is to add multiple streams. So what is the role of hypervelocity stars in all this study? Can they be complementary? Can they help, or are streams enough at this point?
Okay, so this is the plan. Okay, and this the plan of this project, which is actually called Vega P. So I don't know if you see it, but streams are made of bound stars, and they are very good in constraining the enclosed mass. So here in this sketch on the x-axis is the enclosed mass within the radius of the where most of the stars of the streams are, and on the left axis is the scale radius. Let's think about an Navarro-Franke-White, for instance, the scale radius of the halo. Okay, and the streams would give this yellow contour. So you see, the streams are less good in determining the scale radius, for instance. Instead, the hypervelocity stars are unbound stars, and they are not sensitive to the enclosed mass, but they are sensitive to basically an effective deceleration of the potential. Actually, at the parameter m over rs square, and they give a constraint like the blue ones that I'm drawing here. So you see, if you simultaneously fit streams and hypervelocity stars, you can actually break the degeneracy between the scale radius of the halo and the mass of the halo. And this is a really peculiarity of the fact that the stars have different kinematics.
Thanks.
Then I think the next one was Aurel.
Yeah, thanks for the talk. It's just a very short follow-up to what Pedro was asking. So what about other stars sort of in the stellar halo? Could they help too, or is this too difficult to measure?
No. Actually, giants have been used, or globular clusters are used to determine the dark matter or halo mass profile. And actually they're all fine. The thing is that they are still bound to the galaxy, so they provide constraint in the same parameter space as streams, so they are more sensitive to the enclosed mass of their orbits. So really, I think it's more powerful to combine with hypervelocity stars because of they are unbound and what I just showed.
Okay, so next one is Prasanjit.
Hello, thank you for the talk. And I was curious to ask, what is the formation or presumed formation mechanism for these closed binaries? Is it, how well understood is it? Presumably it's three-body and many-body interactions followed by in spiral. And how much do you think how much would that depend on environment?
Yeah, yes, excellent question. So I didn't mention this at all. The current understanding, I think, is that most of the double white dwarf that we expect in the galaxy and we observe comes actually simply from binary evolution through stages of at least one common envelope and one mass transfer, if not two common envelopes. The common envelope is what make these binaries so tight, because to be emitter of gravitational waves, they have to have a period less than 40 minutes. So a common envelope is necessary for that. And in all my simulations, this is the only formation channel that I assume in my stellar evolution code. However, it's also true that they may be formed through dynamical encounters, but this is mainly in an extremely dense environment, probably like the galactic center. And the innermost part of globular clusters. But I haven't actually explored that population in particular.
Okay, thank you.
So while other people raise their hands, I had a question that is actually a bit more technical, but I was curious to know the answer. So the simulations of the Milky Way with the bar that you showed before, so they were they were picked to be as close as possible to the galactic, to have a galactic bar that is similar to the one of the Milky Way, or was it not taken as a criterion to?
Yes. So. So the answer is yes, but since the bar is not well determined, for instance, as I said, the viewing angles is highly uncertain, then is, as far as understood, is in general, the Milky Way simulation reproduce large-scale properties of the Milky Way. And the bar has similar properties qualitatively of what we think are the quality of the Milky Way bar.
Mm-hmm.
But I don't think that has been put on quantitative terms. But what I mean is that probably there are simulations that represent the bar better.
And probably it's not important because for you, the main thing is to show given exactly. A certain distribution well, yeah.
Exactly. In fact, I didn't mention, but we also tried to rotate the bar. So we made the Milky Way, we rotated the bar and we tried to see how well we can reproduce it given a different viewing angle. And we found that only if the bar is actually aligned with our line of sight, we are in trouble. But if there is a little angle, then we can see the structure.
Right, right. And I mean, for the Large Magellanic Cloud, I mean, yes. the next step in the modeling, maybe you yes. said it at the end, I didn't catch it. What is the
oh yeah, so yeah. We use here, so okay, so the next stage is actually this one. So try to so there are two, but one is this one. So form through produce this contour of gravitational wave flux from Large Magellanic Cloud simulations. For instance, we use again Elena Donchia's simulations. And then simultaneously use this map to simultaneously fit optical mass distribution and also dust extinction map.
Okay.
Yeah, I think this is the main one. The difficulty, yeah, and we're using we're using for now the simulation from Elena Donchia again.
So these are still non-cosmological or?
No, I don't think so. No.
Okay. 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 So I think I don't have any more questions. I don't know if other people from the audience. We still have maybe 1 minute for questions if someone has an urgent question. Otherwise, you can also reach Elena by email, I guess.
Yes, sure.
You think about something later.
And thank you very much for having me, and really hope to come.
Yes, we should plan as soon as we know of another good slot. We should plan an in-person visit for you, maybe staying a couple of days at least.
Okay, thank you very much, everybody.
Thank you. Bye, Elena. Thanks a lot. Bye-bye.